So thank you all for coming to Reinforce. It's been a bit of a gap, but it's exciting to have everyone back um, gathered together. Hi, I'm Neha, and this is Andrew. And we essentially work on techniques and services that help you achieve provable security. And today, Andrew and I are going to take you on this adventure of provable security. And I'm going to share our approach and mental model of how we are applying mathematical logic to solve your security problems. Like what I say may sound like science fiction at times, but like the best science fiction, I believe it's predictive of our future and very illuminative of our present. So we'll kick off our adventure with the fundamentals of provable security. Spoiler alert, it's all about universal statements. We'll explain what they are and why they matter. Next, we'll show you how you can use AWS services today to make these universal statements about your security. And that is the biggest takeaway of the talk. And yes, I do mean the universe. And we'll take a peek behind the scenes at the science and engineering that's making this not fiction and very real. And finally, we'll also tell you how Amazon Consumer Payments is using these same services that I'm going to talk to you about to make universal statements about their security. So let's embark on our adventure of provable security. Now, to build our mental model for universal statements, let's start with code. Like when we write code, we think about what it does or that what we intend for it to do. To help gain assurance, there's a lot of things we do. We test it, we do code reviews, we do integration testing, unit testing, AppSec reviews, and pen testing. And the more we do those things, the more we gain assurance that the code actually does what we intend for it to do. But that's not enough, because we want to know for certain. We want to know that the code does what we want in all possible cases. Like we want to know that the code never deadlocks, or we want to know that the particular assertion never gets violated. And that's what I mean when I say the entire universe of possibilities. And that's what a universal statement gives us. It's a statement of fact that holds over an entire universe of possibilities, not just what we've tested or observed or even fuzzed or thought about. Universal statements is across all possible values. And we use words like all, every, each, always. Now you may say, what's the counter of universal statements? And they're mostly true statements. Most of my code is correct. Most of my buckets are secure. It's the sort of statement that may sound good, but it's not really certain. Now, this is just an imagination of like what the universe of possibilities may look like for a piece of code. Here, each node is a program statement, and each arrow is a way to move from one statement to the next. Now, each path in this graph represents a different way that the code can exercise some path in your execution flow. And there are an infinite number of paths because you can have loops in your code, and when your loop iterates, you can have an infinite number of paths. For a graph like this, we want to know, are all these paths good? Are all these intended? Do any of these paths violate one of my universal statements? And wouldn't it be great if we could press a button and find all the paths that violate our universal statements? All the paths, not just a single path, but all the paths. And think about it, a magic button, one that searches the entire universe, all the configurations, all the paths, and does it quickly, because that is key. If you have to actually wait for an eternity, then such an analysis doesn't do us any good. Now, that's the focus of this talk, how you can make universal statements about your applications. What I'm saying, what I was telling you about code is essentially true for cloud applications as well. And most of you do attempt it today, even if we don't use the same vocabulary. You have in mind what you want your applications to do, and you validate this truth by using testing and canaries and AppSec reviews. Again, all the things I said that hold true of the code hold true of the applications that you're building as well. Now, each of these techniques are useful, but partial. And even when you add them all together, you don't cover the entire universe. And so what are your options? You could try to brute forces, like explicitly enumerate all possible values. But that would take several lifetimes of the sun to cover such a big, broad space. So provable security is your alternative. It is about using mathematical logic to prove universal statements about your applications. It does it by turning AWS into math and use mathematical proof techniques to get definitive answer. So let's go on this universal statement adventure. What does this universal statement adventure look like? Now, here's a flight plan for our adventure. We are going to learn how to make universal statements about your security. And if you were to take one picture in this whole talk, this is the slide I would take a picture of. This is the key. This is the roadmap. This is the flight plan. This is the crux of the talk. So what are some universal statements you can make? My S3 buckets are not publicly accessible. There is no unintended external access to my S3 buckets. These are powerful statements. What about EC2 instances? You can say, my EC2 instances are not publicly accessible. You can say, all SSH traffic to my instances goes through a firewall. Now, the key here is each of these statements cover their universe, the universe of possible IAM requests, or the universe of all possible network packets. So let's get started. Show of hands, who's already using S3 block public access? Awesome. So this quote is by you. It's all the folks who had their hand raised. This is your quote, because here's I'm going to show you for the others how you can be making this universal statement too. It's easy. Go to the S3 console, look at permissions for your bucket, and you'll see S3 block public access. And as the name says, when you turn it on, it does block all public access to the bucket. So how does it do it? It applies mathematical logic to the S3 bucket policy and checks if it grants unrestricted public access. And if it does, then it applies an internal lockdown policy to prevent any access from outside your account. And this stays in effect until you change the policy and make it not public. And if your policy is not public, then nothing changes. Everything continues as before. So you can go turn it on today with a click and turn it on for the buckets in your account. You can also do it for your entire account. You can enable block public access to every bucket in every region, in every account. And when you create new buckets, when you have it turned on at the account level, it will automatically apply to all the new buckets that you create as well. It gives you ease of mind. Now, S3 block public access is available at no extra charge, and you should use it liberally. It's applying, if applying it at the account level works for you, do it. But if you're hosting some web assets in an S3 bucket in your account, apply it to all the other buckets where you don't have any need for it to be public. Now, it's a simple thing, but with this simple button, you can make a universal statement that says, my S3 buckets are not publicly accessible. Now, as an experiment, let's try to see what happens if we try to break this universal statement. If we turn block public access on and somebody tries to change the policies, for starters, we warn them that this is not going to work because you have block public access turned on. So before you try anything fishy, just know that you have block public access turned on. And they're like, oh, I'm going to ignore it because, of course, I don't follow the rules and I'm going to try to do it anyways. And when you do, the policy attachment will fail because block public access is turned on. You cannot make the bucket policy, you cannot make the bucket public. And that's the power of a universal statement. It gives you a bedrock of something that you know to be true. So, show of hands, who here is using IAM Access Analyzer? Great. And this code is by those folks who had their hands raised. And if you are jealous of them, then you should be able to state and want to state something more powerful about your security posture and be able to make universal statements. I'm going to show you how you can do it too. Now, before I do, notice that this is a more powerful universal statement than the public access one. It's not just saying that the house is locked, it's actually tracking down everyone who has a key. So to make this universal statement, you go to the IAM console and you can just go turn on Access Analyzer. It's one click, again, at no additional cost. Now, when you enable Access Analyzer, it scans your account or your organization for the supported resources which are accessible from outside your account or your organization. So you have that same capability of like creating a zone of trust for your account or your organization. Each of the category of external access shows up as a finding. So here you'll see that I have two findings for my S3 bucket. The first one says that somebody from an external account can write to this bucket, while the second finding says, hey, this bucket is readable from an external organization. Now, what do we actually do with these findings? So there's a few options. So let's zoom into this particular finding and say, what should we do? The first one is about an external account that has write access, and the detail page shows what actions they have access to, and it provides a couple of next steps on what you can do, because this triage is an important aspect of your security posture. If the access is intended, then I can go archive the finding. Then it won't show up in my active findings. I can still go see it. It never goes away. But now it's clearly marked as intended. Because the keys to your house, there are some people you may actually give to whom you intend to. It's not that they're lost or stolen. On the other hand, if the access is not intended and I need to remove it, Access Analyzer directs you to the S3 console for this bucket where you can edit the resource policy and remove the access. And of course, you can do all of this in the CLI and the APIs as well. Now, once I've changed the policy, I can click the rescan button to immediately reevaluate the finding. And once I've fixed it, I can change it from active to resolved. It'll automatically change from active to resolved. Now, you don't have to hit the rescan button because Access Analyzer will continuously monitor policies for changes. So I could have waited a few minutes and the finding would have updated on its own. But I do like immediate feedback, instant gratification. Now, whether you're marking the findings as intentional by fixing them or by actually marking them as intended, the goal is to get to 0 active findings. 0 active findings can say, there is no unintended access to my S3 bucket. The humans are an important part of the security posture because the tool can tell you who has access, but you, the security expert, has to go in and say, is this access intended or do I need to remove this access? Now, if I have active findings, the most I can say is there is no unintended access except these people, but the decision is still open on the folks who actually have access to it, whether they should or shouldn't. So to really have confidence in your security posture and ensure that only intended people have access to your S3 bucket, you really should go and triage all the findings that show up in Access Analyzer. Now, as I mentioned before, Access Analyzer does constantly monitor resource policy for changes. If we want to stay on top of things, we need to know when these new accesses are allowed. Sure, we could go and periodically check the console, but I'm going to propose a more automated approach. Now, in this slide, I've shown a very simplistic architecture to produce email notifications for Access Analyzer findings. Access Analyzer already publishes findings to EventBridge, so all we need to do is wire it up to SNS. So here, I'm going to create an SNS topic to publish findings to. I'll subscribe to the topic. In fact, I'll subscribe Andrew's email to the topic, so he can be responsible for all the new findings that show up in Access Analyzer. I think that's a really good idea. And now, the only thing is I have to go and create an EventBridge rule. Here, I'll create one that matches Access Analyzer findings, and I'll set the target of the rule to the SNS topic that I just created. And this is one of the cases. This is as easy as it looks, literally. Now, as a reminder, here's the architecture we set up. Now, let's see it in action. So we'll start by changing the bucket policy to grant some new access to some external VPC. Within a couple of minutes, Access Analyzer detects this change. It analyzes this new policies and generates a new finding, which shows up in Andrew's email. We were clever here. We signed up Andrew's email for this. And zooming in, we can see that this message contains various details on the access. When it was first identified, what actions are allowed, if it's allowing public access or not. In fact, nobody wants to read this type of email. This was just for illustration, and of course, because I wanted to give Andrew a hard time and fill up his inbox. Now, what would a more realistic architecture look like? Now, we could use Lambda. It gives us the versatility of looking at the finding before deciding what to do with it. We can use the Lambda to add some logic to do risk assessment. As a first pass, decide how important this finding is. If it's low risk, then the Lambda can archive it. If it's medium risk, the Lambda can send a descriptive email for the right team to fix it. And if it's high risk, the Lambda can just go to the S3 bucket and roll back the policy. Now, we aren't going to work through setting all of this up, but what I want you to do is open up your mind to the possibilities that once we start programming around these access findings, what specific actions will you take depend on your companies and your security needs. But the power here is Access Analyzer gives you the ability to program around your access changes, not just your policy changes. It gives you these descriptive, declarative forms of what access changes. And it lets you work at a higher level of abstraction and get more done. We've talked a lot about Access Analyzer in the context of S3 buckets, but it supports all the resources on this slide. And as we are continuing to add more, Access Analyzer, you can make universal statements about your buckets, roles, keys, functions, queues, and secrets. We'll keep this game on. Show of hands. Who here is using Amazon Inspector? Okay. The same folks keep raising their hand, which is good because, it shows like there's awareness in the same set of people, but for the others, you guys need to catch up. Now, because some of you are getting quoted more than others in the talk, I want to show you it's very easy to get quoted in this talk. It's literally very easy. So you can go to Amazon and inspect. Okay, I dropped my. Oh, thank you. Amazon Inspector is its own service, and it's one click to enable. It's a paid service, but trust me, it's worth it. Amazon scans your EC2 instances and containers to identify vulnerabilities and misconfigurations. It reports these as findings. The type of findings we are going to focus on here are internet accessibility findings. For example, we have shown here that says one of my EC2 instances is publicly accessible on port 22. Now, zooming in, I can see exactly when this was discovered, where the instance is running, what image is on it, and so on. As before, the goal is to get to 0 active findings. And so we need to make a decision here. If it's not intentional, then we need to fix it. The details pane gives us a starting point from which we can go change the ACLs or the network configurations, route tables, or security group that makes this access possible. If it is intentional, we can create a suppression rule for it. And let's do it now. Here, we're going to create a suppression rule. I'm okay with an instance being publicly accessible on port 22 if it's a bastion host. It's easy enough to filter for that and apply the suppression rule. Once I've done it, I have to go and see, oh, I have no active findings. It's the same story as before, only when I get to 0, that I can universally state none of my EC2 instances are unintentionally public. It's a powerful feeling to be able to say that. Now, similar to Access Analyzer findings, we can program around inspector findings as well. But for variety, I'm going to talk about another option here. You can go to AWS Security Hub, which is the central place to aggregate and act on your findings. And you can see this from this architecture diagram that it doesn't get much easier. To do this, you need to enable Security Hub and enable Amazon Inspector integration in Security Hub. And that will allow Inspector to vend findings to Security Hub. Now, what's the beauty in there? Here's what my Security Hub dashboard looks like. Notice that it's aggregating both my inspector findings and my IAM Access Analyzer findings. It's a place where universal statements from these different services come together. Okay, last one. Show of hands. Who here is using VPC Network Access Analyzer? Okay, fewer hands. That's okay. That's all right. That's the point of this talk. If everybody was raising their hand, then this should have been a different talk. But we can all raise the security bar here. Let's see how. Let's imagine we want to build a network that looks kind of like this. We have 2 subnets, both front-ended by a network firewall. And we can clearly see from this picture, all network traffic goes through the firewall. So we are done, right? Not quite. This is just a picture. Let's check out what our reality matches this picture. So we'll go to the VPC Network Access Analyzer, which is available in the VPC console. It's right next to the Reachability Analyzer. We aren't talking about the Reachability Analyzer today, but if you don't know what it is, you should. And whenever you can't figure out why instance A cannot talk to instance B, use Reachability Analyzer. It's backed by the same mathematical logic as the services that we've been talking about today. And so if you want to get definitive answers about how debugging your instances, Reachability Analyzer is your answer. And it's definitely saved me from some headaches. For today, we're going to go back to Network Access Analyzer, or what like we call it NA2. Now, NA2 is built around this notion of scopes. A scope is a way of saying, show me all the paths from A to B that don't go through C. So for our universal statement, we want to see all the paths from an internet gateway to an instance that do not go through a network firewall. Simple enough. Now, what do we do next? We just click a button. Remember the magic of the button? All we wanted was a button, a magic button. And you click analyze, and it looks through all my VPCs to identify every internet gateway, every instance, every path between them, and then filters out the ones that go through the network firewalls. Of course, it's using clever mathematical logic to do this efficiently, and we'll get a taste of the details of why it is clever math and not just magic or voodoo in the next section. And what VPC, when the analysis is done, we get a very pretty summary. And we says, hey, here's all the paths that match our criteria. In this case, we just have one. But that's unexpected. If you remember our architecture, it looked nice and clean. Everything was going through this network firewall. What went wrong here? And we just thought that there were no other ingress paths, so we need to investigate. So pulling up the details on this path, we can actually see what went wrong here. From the internet gateway, through the route table, the access control list, the security group, and finally the network interface. Clearly, there is no firewall along this path. And if we hover around the network interface, we see the details it's connected to. In this case, it's server 3 in subnet 2. So what it means is this is what our actual network looks like. The SSH traffic from the internet gateway to server 3 is routed around the firewall instead of through it, and our universal statement doesn't hold. We aren't going to spend time here to fix it, but I think you have this idea by now. And the most important part is when we do fix it, we know universally that the ingress SSH traffic that avoids the firewall is actually fixed. We just don't think it, we know it. We know it for certain. Now, I talked about one example. There's many others. When you create a scope, they have a bunch of templates where there's suggestions on how to get started. It's like a tasting menu of universal statements, just waiting for you. And you can make universal statements about ingress, egress, trusted networks, restricted traffic segmentation, or you can choose your own adventure. If you're serious about knowing this security posture of your network, then I would strongly encourage you to start to use Network Access Analyzer. And if you want to know more about Network Access Analyzer, there's a breakout session later today, which focuses on the different aspects. It covers many more use cases and even includes a customer story. So it's today between 4:15 and 5:15. So please check it out if you want to know more. So coming back to our flight plan, this time annotated with our top tourist destination. I had mentioned if there's one slide that you want to take a picture of earlier, this is the same slide, but annotated with which of the services give you that capability. So if you missed the chance to take a picture in the earlier time, again, this is your second time. This is your opportunity now. And really, please, please, please go turn on S3 Block Public Access, go turn on IAM Access Analyzer, go turn on Amazon Inspector, and go use Network Access Analyzer. So how does it work? Is it just science fiction? Is it even possible? Am I just making stuff up? Now, so let's look behind the curtain and see how the magic is actually made. Now, let's imagine we have this policy here. It's allowing get object access to an account and then denying some of that access. Suppose we want to know a universal statement such that my bucket is only accessible from inside vpc-abc. And we want to know that this is true for every possible request in the universe. It's a lot to ask for. There's an infinite number of requests in the universe. So how do we do it? We'll start with a single request and see what happens. This should seem familiar. When a request comes into AWS, it has a lot of data associated with it. The principal, the action, the resource, the date, the time, the IP address. And the authorization engine in AWS tries to match the policy with the request. First, it will check whether the principal in the request matches the principal in the statement. If it does, then it checks whether the action matches. If it does, then it checks the resource, and so on and so forth. And I'm guessing this is a mental model that you're familiar with. And keep it in mind because this is going to be useful, but things are going to start to get a little weird. But hang on. Now, there was only a single request. How are we going to do it for a universe of requests? It sounds huge and impossible, but here's the first key idea. Like before, we are going to send it one single request, just one. But it's a special request. It's blank. It's empty. In a way, it represents all possible requests. And in automated reasoning jargon, we call this request symbolic. It's not really a request, but a stand-in for all possible requests that you can get by filling in the blanks. The idea is that we will see what happens to this request and therefore know what happens to every request. So let's get started. We'll match the symbolic request against the policy. Does the principal 1, 2, 3 match? The answer is sometimes yes and sometimes no. Now, so we are a little bit stuck. But notice, there's only two options. Either they match 1, 2, 3, or they don't match 1, 2, 3. So that's the next key idea. Using this, we can say, we can split the universe in half. In one half of the universe, the request match 1, 2, 3, and that's again represented by a symbolic request. In the other half, all the requests that don't match principal 1, 2, 3. But those requests are not allowed by our policy. So we can color them white and set them aside. And you can see this is how we've partitioned the universe effectively. I want you to just take this in and convince yourself. And we'll continue to do that. Now we'll do it with action. What are we going to do here? Does it match get object? Yes and no. So what are we going to do? We split again. We're splitting the universe. In one half, we have all the requests that match principal 1, 2, 3 and action get object. In the other half, we have all the requests that match principal 1, 2, 3 and don't match the action get object. Now the second half won't match again, so we can color it white again and set it aside. You see what we're doing? We're reasoning about a universe of requests, but we are doing it effectively, efficiently. And we can keep using this pattern, the same story for the resource. Some will match and some don't. So we'll split the universe again. We'll color the ones that don't match or are not allowed white. And finally, we look at the deny statement and specifically on condition source VPC. This splits the universe the last time, and half of those are not allowed. So at the end, we've split up the world of possibilities into all these bins, and every possible request falls into exactly one of these. Now, rather than look at nearly infinite universe of possibilities, all we have to do is look at these 5 bins. This is where the clever math comes into play. For example, all these requests in the white ones that are not allowed, so they don't make the bucket accessible outside the VPC. And the requests that are allowed here, they are from the VPC. So again, they're not accessible from outside. Therefore, we can conclude that the bucket is not accessible outside the VPC. Now, what makes this answer powerful is this universe concept. It's covering the entire universe of possibilities, but doing it in a short amount of time. This is how we get our arms around the entire universe, so we can accurately say something about it. Now, just to go an inch deeper, I'll show you the mathematical encoding of the policy that we use. If you squint a little, you'll see how this actually represents the original policy. Just have to squint a little bit more. But there's no more rules about allow and deny overlap. Instead, it's all baked into the mathematical representation. And there's no rules about which conditions are ANDed together or ORed together. We've taken into account all the rules of AWS policies and encoded them into math. We can turn this over now to a specialized mathematical solver to tell us if there exists a solution to this math problem. Now, once we see how this works for a single policy, we can scale it up. We can do it for each region, for each account, for each resource, for each policy change, for each mathematical solver. I haven't even mentioned this yet, but we have multiple solvers running in the back end, racing to see which can compute the correct answer first. The math solvers are competitive too. You didn't think of that one, did you? So as a result, we have 1 billion queries every day. It's 1 billion universal properties, all in the name of provable security. If you want to learn how this actually works, want to go deep, we have peer-reviewed publications that go into the nitty-gritty. The one on the left describes how the policies are encoded into math, while the one on the right says how Access Analyzer adds a twist on top of the underlying encoding. Let's look at one more example. We're going to see how this same reasoning looks like for networks. Here, we have a simple network with a bastion in one subnet and a web server in another. So all we want to do, simple thing, all we want to do is prove that all SSH Ingress goes through a firewall. Now, take a moment to convince yourself that it is true. And pay attention to how one would reason about it. We're going to use the same key idea. In order to look at what happens, we're going to look at all possible packets through one symbolic packet. We'll look at this packet, and as it comes through the internet gateway, because it's coming into our VPC, we can already start to fill in part of the packet. We know that its destination IP must be in the CIDR block for our VPC. As it comes in through the route table, which determines which subnet it should get routed to, here the universe splits into 3 parts. There are packets that are bound for subnet 1, packets bound for subnet 2, and then there's the rest. So these other packets are going to be dropped, so we color them white. Now let's look at what happens to the packets bound for subnet 2. as we apply the network ACL for the subnet. Here, again, we split the universe into half. It separates the packets destined for port 443 from all the other packets. And all these other packets are blocked by the ACL and drop, so we color them white. You see the pattern. We're splitting the universe, and everything that doesn't match, we're dropping, coloring them white. Now, we have enough information to prove our universal statements. These packets are on port 443, so they are not SSH. And these packets include SSH, but we know that they go through the firewall based on the route table. So our universal property is true. Our universal statement holds. It is true for the entire universe of packets, which only required us to look at 4 different types of packets, very special types of packets. We call them symbolic packets. Now, here's another peek of what behind the scenes of what the encoding mathematically looks like. Notice that we convert the rules of VPC networking into math. All the details about the order in which the route table rules are applied or the order of the network ACL rules is baked into the math. It's baked into the logic. And again, we can hand it off to a solver who knows nothing about what a VPC is. Finally, I want to talk briefly about how this scales up. All this splitting of universes sounds reasonable, okay, but in practice, it can lead to an exponential blowup, even in the presence of this symbolic packet notion. And because we need to scale up to networks that are tens of thousands of instances, so how do we do it? The way I described about splitting the universes was based on following a symbolic packet as it went through a network through like a real traffic, front to back. But the beauty of this reasoning is we are not limited to that. I could have taken the same symbolic packet and instead traced its route backwards. This would have caused the universe to split in a very different way. Because we look at the NACL first and then the route table, it would have led to more splitting. But in general, the ability to pick when and where we split the packet is vital for performance. We use this ability to split the universe in the most efficient way, even if that corresponds to a packet traversing the network from the middle out. And that's the power of the reasoning techniques that we use, that we can do it in these different ways. If you want to know more about the mathematical details, we have 2 peer-reviewed publications shown here. The one on the left talks about the engine underneath this analysis, while the one on the right talks about the additional twist on this engine used in Reachability Analyzer. I've been focusing a lot on the customer-facing provable security in this talk, but we've been doing a lot more in our own systems as well. In addition to policies and networks, we've used provable security to look at our own code and algorithms and protocols. If you want to know more, I would recommend going to the Amazon Science website, and specifically the section on automated reasoning. Here you'll find all our peer-reviewed papers. There's also a dedicated provable security website with links to blogs and videos. Now I want to hand it over to Andrew, who's going to talk to you about how this work is being done and used in Amazon Consumer Payments.
Thanks. All right, hi, I'm Andrew Gasick from Amazon Consumer Payments. The first thing to understand about us is that we are an AWS customer, just like you. And we haven't always been. It's new for us. It's a journey, like it is for most people. And I'm here to tell you how provable security fits into that journey. So in consumer payments, we're responsible for credit card numbers, bank account numbers, billing addresses on millions of customers spread all across the globe. And traditionally, the way we've kept that secure is through a custom, on-premise, isolated environment. It wasn't air-gapped, but it was as close as possible while still being usable. For instance, operators had to drive to the network data center to do updates. And the servers were kept in separate cages within the data center. In fact, Amazon rented out year-round lodging near the data center for on-call operations. We're now moving that environment from the air-gapped system to AWS. So from nearly air-gapped to in the cloud. And I'm going to tell you about how we're using provable security to get the same level of assurance in that environment as we had in the older, less easy to maintain environment. So let me explain how this fits into kind of the broader Amazon payment ecosystem. You go on the Amazon.com website, and you put in your credit card information. That's sent to our web server, encrypted over HTTPS. And the first thing we do before anything else is we re-encrypt that data with a key that only Lumos has, and we send it to Lumos. And now we've securely stored your payment information. It'd be great if we were done there, but we eventually have to use this information in order to purchase things on Amazon. So how do we actually make use of this information? Well, Lumos sends back an opaque token. It's randomly generated. It has no meaning whatsoever outside of Lumos, which means we don't need to be as paranoid about it. If an attacker somehow got hold of this token, they can't infer anything from it. They can't do anything with it. We then send that opaque token to all of our other payment services throughout Amazon. Time goes on, sometime later, you click the Buy Now button, and what we'd like to do is we'd like to send a payment request to the bank. But the problem is that we only know the token, and it doesn't have any meaning. So instead of going to the bank, we have to go through Lumos. We send the payment request into the Lumos environment, and it has the token in it. And then Lumos takes that request, it de-tokenizes it, it takes the token and replaces it with the actual payment critical information, and that's what gets sent to the bank. Okay, if you want to know more about how that all works, how firewalls are set up, how we partition the space in terms of teams that operate it, there's a talk for you from reInvent in 2021. Just search for Lumos and reInvent, you'll find it. I'm going to talk about the provable security aspect. So for starters, here's that slide Neha showed. And as you saw during the talk, I was raising my hand when she was asking, because we use all of these services. We use S3 block public access to make sure our buckets aren't publicly accessible. Everyone should be using it. We use Access Analyzer to look for cross-account or cross-org access. We use Inspector for vulnerability scanning and for network reachability checks. And we've just started using Network Access Analyzer to look for internet ingress across Lumos. And what I'm going to talk about for the rest of this time is how we're going deeper with provable security, how we're trying to combine some of these universal statements. And to do that, we need to talk about customer data. This is a little bit of an uncomfortable conversation, but this is the most important thing that we keep at Amazon. And if you take nothing else away from my talk, the most important thing is the mindset about it. We treat customer data like it's radioactive to us. And this may sound a little bit weird, right? Like, why do we keep the data away from the engineer? Aren't we worried about the engineer having access to the data? And the problem is, if you just think like that, biases creep in. You say, oh, I trust this team, I trust this person. It's okay if they have some of the data or some access. If there's some way they could, exploit a misconfiguration to get it, that's fine. But if you think of the data as radioactive, then the biases go the other way. I really like this team. I don't want to accidentally expose them to customer data. That's going to be a mess they're going to have to clean up and scan through their logs. This is the most important thing when it comes to customer data. So what do we do about it? Well, we build a containment unit out of AWS. We use identity and access management. We use virtual private cloud and AWS organizations to create a containment unit for the critical data to ensure that it can't get out, that there's no cracks, there's no misconfigurations that could lead to problems. Because what we're trying to do is ensure that exposure is not even theoretically possible. Even if someone acted maliciously or did something unintentionally, they're not going to be accidentally exposed to customer information. This is the boundaries of provable security. It's not just IAM or VPC, but it's protecting customer data. Here's the provable, the proposed universal statement that we want, that we are never unintentionally exposed to customer data. Now, it may seem strange to see the word unintentionally here. Why would we ever want to be exposed? Unfortunately, it is necessary in the case of, say, a fraud investigation. But even there, we have controls in place. Think of it like a virtual Geiger counter, which says, oh, this person's been exposed too much already. We better make sure they don't get exposed anymore today. Now, how do we go about actually proving this universal statement? We're developing a system that I'll call the critical zone. This is mapping out all the places where critical data is used within Lumos, where that data can go and where it can never go. If you think of Lumos like a nuclear power plant, then the critical zone is the reactor. It's where the nuclear fuel is, but also everything contaminated by it, the control rods, the coolant. Here's what it looks like in practice. In Lumos, as I said, we generate these opaque random tokens, and we have a mapping from customer data to tokens. And we store that in the token table. So this is definitely critical customer data. This is in our critical zone. It's the nuclear fuel. And now we apply policy analysis, the same analysis that underlies IAM Access Analyzer, to figure out who has access to that critical data. In this case, there's only a single role with access. It's the tokenization role. And we ask ourselves, does this connection, does it carry critical data? And here the answer is, well, of course, yes. That's the whole point of the role, is to read from the table and to write to the table. So we expand our critical zone to cover that role, which means, as a consequence, we're also expanding the boundary of the critical zone. There's a cost to making this bigger. This tokenization role, it has a lot of other permissions. Access to logs, certificates, metrics, KMS keys, secrets, the cluster. And so now we need to go through and look at all of those possible risks. For example, we look at the connection to the metrics and we ask ourselves, does critical data go along this path? If so, we would expand our critical zone. In this case, we're saying no. It's only intended to send high-level metric information. So we put controls in place to ensure that critical data doesn't go out. And in fact, whenever we do this, we always use two controls. One preventative, like code review or code analysis, and another detective, in case anything were to get exposed. Coming back to the role, we then look in a different direction. Say we look at this tokenization cluster. Well, this is the compute substrate on which the role runs. That cluster is allowed to assume the role, so it has to be part of that same critical zone. So here we grow the critical zone, and as a consequence, we grow the boundary. And by doing VPC network analysis, the same analysis under Network Access Analyzer, we discover other network endpoints that it has access to. Network canaries, maybe some VPC endpoints, and also the transmission cluster. This is the cluster that's actually responsible for sending payment data to partner banks. And we continue, we iterate here. We expand our critical zone, figure out where we need controls and what's actually in the critical zone. And this is what our system really allows us to do. It allows us to map out where critical data is, who might possibly be exposed to it, and then it allows us to go in and make changes based on that. We might say, yeah, this exposure actually happens. Critical data does go from here to here. That's the worst case scenario, but it happens because your system is handling critical data. And then the boundary grows. Or, slightly better, we say, no, critical data doesn't go over there. We'll put some controls in place, we'll monitor it, we'll make sure that there's never any critical data there. Or the best possible case is when we say, in fact, we don't even want that connection to be possible. We go in, we change the IAM configuration or the VPC configuration, and we remove that access. We shrink the boundary of the critical zone. As I said, that's the best possible case. In practice, what we find is that the critical zone is really just a small part of our AWS architecture. Just like if you had a nuclear power plant, the reactor is only a small part of it. You also have generators and pumps, turbines, cooling towers, transformers. You have control panels, offices, even the parking lot. Just a lot of infrastructure around to support the core function. And it's the same in AWS. We have roles for logging, for metrics, deployments, operator roles, integration tests, canaries, just a lot of stuff to support the core business. But using the critical zone, we can actually identify what are the pieces that we need to monitor and what are the places where we don't need to worry as much. That's the idea behind mapping out the critical zone. The idea is to know where all the critical data is, where it can go, where it can never go. And that's how we achieve our universal statement, that we're never unintentionally exposed to customer data. This is where I see the future of provable security. Not just stating things about your IAM policies or your buckets or your VPCs or your instances, but stating things about your most critical assets. Thank you for attending the talk. If you have any questions, Neha and I will be up here for a little while afterwards, and then out in the hallway once they kick us out of here. You can also reach out to us by email or on social networks. And please remember to fill out your session surveys. These really do matter to us. We read every comment. We look at every score. They affect what talks are given and who gives them. Thank you.